Okay, so in this lecture, we will be discussing redundancy of manipulators or redundant manipulators. And in this, with particular reference to kinematic redundancy. Let us see what it is. And whenever the issue of redundancy comes, optimization immediately appears in the scene. In fact, uh, what this document does not contain, but preferably should have contained, is the name of the book from where this material has been compiled. The name of the book is Redundancy and Optimization by Yoshihiko Nakamura, Nakamura. So what has been given in this compilation is the subject matter of chapters 3 and 4 of that book, Redundancy and Optimization by Yoshihiko Nakamura. Apart from this, the chapter 9 of that book is also useful. So you can try to find these things. Now to go about the subject matter, I think it may be a good idea if I put it full screen. Yes. So how and in what ways redundancy and optimization appear in robotics? First of all, the kind of redundancy that we are going to study in detail is the kinematic redundancy, that is redundancy of motion. That is a higher degree of freedom of motion is possible by the manipulator compared to what is bare minimum necessity. Okay, so where the task space dimensions are less than the degrees of freedom of the manipulator. Okay, so such a situation will make the manipulator a kinematically redundant manipulator. That is, the redundancy is redundancy of motion. Okay, there is more kinds of motion possible than necessary. Okay, so typically you would say that in general, to manipulate an object in 3D space, you need 6 degrees of freedom in the manipulator. The way you get Puma robot or Stanford manipulator, okay, or Cincinnati Miracron, so or KUKA for that matter, these are typically 6 degrees of freedom manipulator. Some of these, for example, some of the modern manufacturers may have 7 degrees of freedom manipulator also, and that will be a redundant manipulator. So if you have a 7 degree of freedom manipulator or 8 degrees of freedom manipulator, 9 degrees of freedom, then you call that manipulator as a redundant manipulator. And since the redundancy is in motion, so you call it kinematically redundant. Okay. Now, if we have more kinds of possibilities than bare minimum, then where do we use them? Okay. So in avoiding obstacles, sometimes more degrees of freedom help. Okay. So rather than a small number of joints, if you have a large number of joints like a snake's body, okay, which is actually completely flexible, okay, but even if it is not completely flexible, but if suppose rather than 6 bigger links, you have 14 smaller links, okay, then in more possible ways you can accomplish some motion, and therefore you can choose which possible motions avoid an obstacle. Okay, so another is singularity avoidance. Singularity is a problem which we have discussed while studying the kinematics. Okay, so you can avoid singular configurations because that is not a configuration which you have to pass through necessarily. You can choose another way to go about it. Okay, and sometimes you can improve reach and maneuverability. Okay, now these are uses or advantages which you get from redundancy. But just because you have redundancy, you have some task to do. Okay. So if there are more possibilities of configurations than you need, for example, you need one configuration. In a non-redundant manipulator, ordinary manipulator of exactly the correct number of degrees of freedom, you will have a multiple configurations possible to reach a point in the task space. And from a multiple solutions, choosing one is not very difficult task. Now you have infinite solutions. Okay, so you have to choose one out of that. So in a way, redundancy resolution is a rich man's problem. So the choice of one solution out of infinite possible solutions is called the redundancy resolution. You resolve the resolution. You work out an action plan to choose one out of infinitely possible solutions. And there comes optimization. Okay. So whenever you have a choice from an infinite possibilities, then you feel like choosing the best. And optimization comes into picture from there. So it's a rich man's problem. So lots and lots of options possible, and you have to choose some. Okay. So it's a rich manipulator having more degrees of freedom than necessary. So the choice comes as a trouble for the algorithms. Okay. Now, in what domain you have to do this resolution? In velocity domain or in position domain? Now, if you have to do it in position domain, then for a particular position or for a complete path. So these are the questions which we will try to address. Before we go about doing that, we need to a little talk about what other kinds of redundancy would be possible. Because we said that this is redundancy of motion, kinematic redundancy. So what other redundancies are possible? So these are the other kinds of redundancies. One is force redundancy. That cannot appear in a serial manipulator, the kind which you have studied till now. That is possible in parallel manipulators. Okay, where rather than several motions together constituting the end effector motion, in parallel manipulators, several constraints try to constrain the end effector in a particular trajectory. So these constraints operate parallelly, and therefore the redundancy is not of motion but of force. We will see that in the parallel manipulator discussion. Then there can be actuator redundancy. Even in serial manipulator, there may be closed loops for enhancing the stiffness. Some constrained loops may be there. And in such a situation, there may be a possibility of putting more actuators at different joints compared to what is necessary. And then you will have actuated redundancy that for a particular degree of freedom, to actuate a particular degree of freedom, you can use one actuator or another actuator because you have put more. And that is actuator redundancy. And there the redundancy resolution would mean the choice of this actuator or that actuator or a distribution of torques at the different actuators. Okay. So in a way that has some relationship with force redundancy. Okay. There is another kind of redundancy which is sensor redundancy. Okay. So if in order to determine something, 6 sensors are good enough, okay, you may put 8 sensors, okay, at different places. And that will give you, that will first of all simplify the mathematics to solve your problem, okay. And besides that, it will give you an error correction mechanism, inbuilt error correction mechanism. It is like having 8 equations in 6 unknowns, 8 consistent equations or almost consistent equations up to the experimental errors you see. Okay, so that is called sensor redundancy. So fine, let us see how it works. So this point onwards, we will be discussing kinematic redundancy. Now, for a 6-DOF manipulator, this will be the task space vector. The end effector you can manipulate either in XYZ position or alpha, beta, gamma orientation. More than that, motion possibilities are not there. So at most you can have 6 task space coordinates. So it is the task space dimension is at most 6. Why I said at most? Because the manipulator may be planar, in that case only 3. Or the manipulator may be spatial, but there may not be any sense in rotating the tool about its own axis. For example, if the tool is like a cylinder, a pen kind of thing, okay, or a rod kind of thing, whether you rotate it about its own axis or not, it doesn't matter. Okay, so in the task space coordinate, that particular angle will be actually missing. Okay, so that is why it is at most. Now the joint space vectors in the serially connected open chain manipulator, theta 1, theta 2, theta 3, theta 4, as many of them are there. So up to theta n. So task space dimension is n, same as the degree of freedom. Now n can be larger than the task space dimension m. In that case, you have kinematic redundancy. So the forward kinematics that you have is r equal to f of theta. Now theta is too many and r is at most 6. Okay, r coordinates like this. So that means this system of nonlinear equations will typically have infinite solutions. Okay, typically I said because it is not necessary, it may not have a solution for that matter. Okay, it's nonlinear equations. If you suggest a point as r which is outside the workspace, then it will not have solution. But typically within the workspace, when you give some r, typically you would expect infinite solutions. So you differentiate it for a particular theta and corresponding r. You differentiate it and get this. This is again a system of m linear equations in n unknowns, n velocities. Okay, if this is specified. Okay, so that will again have infinite possibilities. I think, yeah. So either you talk in terms of velocities or you can talk of small motion. It is the same thing because it is the same Jacobian matrix which does the mapping. Now this Jacobian is then an m by n matrix. That is less number of rows, more number of columns. A fat matrix, not a tall matrix. And this is a linear transformation from Rn, that is space of delta theta, to Rm, space of delta r. Now you can talk of the quality of the Jacobian. The way for a square matrix, you could talk of the condition of the manipulator, a condition of the manipulator or condition of the matrix as it's how far it is away from singularity. Singularity is a bad thing, you see. So similar thing here will not be singularity because the matrix is not square, but it can be identified with the singularity of JJ transpose, which is a square matrix, okay, of size m by m. So therefore, you can put this quality index MOM called measure of manipulability. Okay, at singularity, the manipulator is hard to manipulate. Okay, so away from singularity, it is easier to manipulate. So similarly here, rather than talking in singularity, you talk of rank efficiency. Okay, or ill conditioning, you can still talk about. So determinant JJ transpose square root. That is essentially the product of the m singular values of this matrix. Okay. This large will mean that it's at a good quality. The configuration is good, where manipulability is high. Okay. Easier to manipulate. The other way of measuring the Jacobian quality is to take the ratio of the maximum singular value to minimum singular value from here. Okay. Now, this is actually a better measure in a way. and this is here small is good. Okay, so this is actually a better measure because it is a dimensionless number. Okay, here you may turn out to be wrong if your units are, you know, large or small. Okay, there will be a big difference. So for example, while measuring things in 1 unit, if you find this small and then say, okay, I'll change the unit so that everything becomes 10 times higher. And then this whole thing becomes 10 to the power m times higher. So immediately you get a large number, but that doesn't mean anything. Okay. So that way, this is actually a better measure, more robust measure. However, this has a problem that this is not differentiable. So if your algorithms are going to use differentiation or derivative based techniques, then this will create problems. Okay? In that context, this is better. So as a measure, this may be better, but as a mathematical quantity to handle through calculus, this has an advantage, and this is the trade-off. Okay. Now, this is a rectangular matrix. So whenever you need its inverse, you don't get it, but you can work with an inverse kind of thing called pseudo inverse, which is denoted by J hash. And linear algebra will tell you what is a pseudo inverse. Basically, from the singular value decomposition of the matrix, if you try to invert it, then wherever there is a zero singular value, in place of that, in place of 1 by 0 in the inverse, in the corresponding place, you actually write 0. Okay. So that way you define pseudo inverse, which has a lot of beautiful qualities. Okay. All related to optimization. I'll talk about that as we come at the correct spot. Okay. Now, we talked about redundancy resolution may be attempted in velocity space or in position space. And in different situations, you will have different tasks. Your tasks will be cut out in different ways. So suppose, to begin with, we consider the redundancy resolution in velocity space. So known is manipulator configuration. Because we are talking about doing the analysis in velocity space, that means the position analysis is complete already. Otherwise, what velocity will determine? So manipulator configuration theta is completely known, and therefore R is completely known. Joint space position, task space position and orientation of the end effector. This is all known. Of course, the design parameters of the robot are certainly known. Then what is given? Differential motion of the hand, delta R, or motion rate, R dot. One of them is, the same, they are mathematically equivalent. Okay. And you want to find out delta theta from this. That is, you want to find out the joint motion. That is, the manipulator is at a particular configuration, and at that configuration, thetas are known, end effector position R is known, and then you say, I want this little end effector motion, delta R, what joint motion would be needed. Infinite possibilities are there, okay? Because this is a rectangular system with less equations in more unknowns. So infinite solutions are there typically, okay? So infinite possibilities are there. However, there is no guarantee that there will be a possibility, because even among them, it may be that some motions are not possible. Okay, such a thing is possible, but most of the time, in an interior point of the workspace, such things don't happen. Okay, so typically there are infinite possibilities. When you try to find out one working solution, then this gives you a very good candidate for one working solution. And what is the spirit of this solution? Rather than J inverse, here it is J pseudo inverse. Okay, if it were a square matrix, square non-singular matrix, then you would have J inverse delta R. Here it is J hash delta R. It is a pseudo inverse. And what it does is that if this system of equations, what pseudo inverse does, or the pseudo-inverse solution J hash delta R gives you. So if this system has conflicts, okay, if it is inconsistent system, then this solution would minimize that inconsistency in the least square minimization sense. And in that least square minimized solution, if you still have infinite solutions, you are bound to have, okay. Or if originally there were no conflict and infinite solutions were there existing, in both of these cases, infinite solutions will happen anyway. Either this itself will have, or the least square solutions will be infinite in number. So out of those infinite solutions, this is that solution which is of least norm, for which delta theta norm is minimum. Okay, so this gives you the smallest possible joint motion which achieves that delta R, either exactly or in the least square sense if there is conflict in the beginning in the system of equations. Okay. Now, how this J and J hash, the Jacobian and pseudo-inverse of the Jacobian, operate in the velocity space in the joint side and in the task space side. So we have already seen that J theta is a mapping that maps delta theta to delta R. That means this n-dimensional Euclidean space to this m-dimensional Euclidean space, Jacobian is a mapping. In this, there will be a subspace which we call as RS, redundant space, okay, which maps there to 0. Okay, it will, I mean, that is a null space. Okay, and that is why there are infinite solutions, because there is a non-trivial null space. So if you have one solution taking you somewhere, that solution plus a member of the null space will also take you to the same point. That is why for every delta R on this side, you will have infinite solutions. Okay. So that is the null space of the Jacobian is called the redundant space. Okay. Now, the whole thing, wherever that maps in this space, that is called the manipulable space. That is all those delta R's which are in the range of the Jacobian, they together construct the range of R, range of J. Okay, and that is called the manipulable space. That is in the task space, those velocities which are achievable by some delta theta. They are the manipulable space. That is, in that subspace you can manipulate. In most configurations, this would be the complete space of delta R. Okay, fine. Now on this side, the redundant space will capture some of the dimensions of the delta theta, that is Rn. You can take all vectors orthogonal to this subspace and they will construct the orthogonal complement of the redundant space. Okay, and that is the orthogonal complement of the null J, right? And therefore, when you multiply a task space vector delta R, task space motion vector delta R with J hash, you get only a component in the OCRS, because it is going to minimize the size of delta theta, and out of two orthogonal components, if one doesn't matter, okay, one is in the redundant space which will anyway map to 0 and the other matters, so only the other will remain, and that is why in the range of J hash it will be only the orthogonal complement of redundant space. Okay. And similarly here, whatever is in the manipulable space, those delta R's which are images of some delta theta and therefore of infinite possible delta theta vectors, its orthogonal complement in this direction, in this space, will be those vectors which constitute pure conflict in this system of equations. Okay, and therefore these are orthogonal. These are in the orthogonal component complement of the manipulable space. Okay. So basically, these are orthogonal decompositions. The domain can be orthogonally decomposed to RS, which maps to 0, and OCRS, okay, which gives you some proper delta R motions. This task space motions possible have two orthogonal decompositions, two orthogonal components. One is in the manipulable space, those motions which are possible, and one in the orthogonal complement to manipulable space, those motions which are not possible. Okay. Fine. With this, we now go about redundancy resolution in velocity space when we can achieve through which we can achieve more than just satisfying the velocity requirement. Let us see how. Say the task specification has something like this: to reach a particular position with a given orientation, okay, while avoiding collision and minimizing joint motion. Now, all this, suppose we bring it to the position, from the position domain to velocity domain, that is to reach a particular position with a given orientation, etc. So this position and orientation, if we consider as small changes, with the understanding that somewhere close we already are in the previous time step, in the previous configuration, and now we want to go to the next time step, next configuration, where this much change in the position, this much change in the orientation we want, and we want to continue avoid collisions, for which also there will be some equations. If the equation already available is in terms of positions, then we differentiate and we can get then corresponding equations in terms of velocities, and minimizing joint motion, which we know how to do. Okay, just take the pseudo inverse. Fine. Now we can attach priorities to these different aspects of the task. Okay. So suppose avoiding collision, we accord highest priority. Fine. To reach the position, we accord second priority. To reach with some orientation, we give the third priority. And finally, if some degrees of freedom are still left to address something more and we do not have anything, then we say beyond that, just minimize the joint motion. Okay? So suppose these are the four priorities. Now, this redundancy resolution scheme operates according to orders of priority, which we have set. So for each order of priority, we have some position relationships. Okay? And based on that, we can work out the velocity relationships, and partial Jacobians come into picture. Okay. So we could have written all of these together. Okay. So some bunch of equation from here and some bunch of equation and some bunch of equation and some bunch of equation together we could have put. And together we could have solved. But then that might have ended up doing something for priority 4 and priority 3, even without satisfying priority 1 and priority 2 completely. So that we want to avoid. So we break down the thing in terms of the partial tasks and partial Jacobians. Okay. And this is just differentiation, nothing very esoteric. Okay. So we first go about to satisfy the top priority requirement. And since only a few equations will be here, since only a few equations will be there and large number of unknowns, therefore this solution you will get very easily as J1 hash delta R, and you can add something more. Okay. Add something more means what kind of things you can add? You see, where will J1 take a Y? Okay. This Y, if you take in the space of theta, delta theta, then Jy into that Y would take it to the delta R space in the manipulable space. Okay, because outside manipulable space it cannot project, and from that manipulable space, as it is inverted back by J1 hash, then actually you should get Y back, but you do not get Y back. Only that component of Y you get back, which is in the OCRS. The redundant space component you lose in the process. And therefore, if you subtract this matrix from En, then that would give you what? That would give you only the component in the redundant space. And that means that any Y, when multiplied with this matrix, basically gives you a delta theta, which is in the redundant space. That means this component attempts delta R1 as best as possible, and this component of delta theta actually leaves delta R1 unchanged because this belongs to the redundant space. Now you can say that this n by n identity matrix is known, this is known, this is known. Now Y we can choose as anything in this description of delta theta, and any Y here will give me a motion which satisfies this without any problem, just as much as this did, because this falls in the redundant space of J1. So now we try to put some suitable Y which we can use in satisfying the lower priority tasks. Okay? So now we put J2 theta into delta theta equal to delta R2, the second priority velocity relationships. And here in place of delta theta, we put that big expression. Okay, this part satisfies the first priority, and this part does not damage that. Okay, does nothing for the first priority. So now here everything is known in this except Y. So what we do? We take this part J2 J1 hash delta R1 and subtract on this side, get this. And then what is left here? It is left this. Now this J2 times this projection matrix we call J2 hat. And this whole thing on this side we call delta R2 bar. Okay. And then solve this system. Okay. Now again, here Y will be J2 hat pseudo inverse into delta R2 bar plus something in this fellow's redundant space, which would be similarly En minus this fellow hash into this fellow into some Z. Now this will mean that this part will attempt delta R2 as best as possible without disturbing delta R1, and this may not be as good as the satisfaction of delta R1, because when we attempted to satisfy delta R1, all the degrees of freedom were in our hand. Okay. Now some of them have been already taken by the top priority task, delta R1. So this one may or may not be satisfied to the dot. Whatever it is, we accept, because for this we cannot disturb the solution of delta R1, okay, which is higher priority. So this component attempts to satisfy delta R1 as best as possible without disturbing delta R1, and this component will leave delta R1 and delta R2 unchanged, because from being in the Z multiplied with this being in the redundant space of J2 hat, it will not change anything in the second priority task. And since we already know that any Y there in the original, which we have used here, would not hamper the delta R1 task. Okay. So this is the component which will leave delta R1 and delta R2 completely unchanged. Now, it may happen that not much degree of freedom is left anymore. How? You see, the third priority requirement, for that you can similarly do from here to here that much of little bit of analysis and get delta theta equal to this, where you put y as this, and then you get this to satisfy the first priority, this to get satisfy the second priority, and this to satisfy the later priorities. It may happen that the content of this is nothing. Why? Because this is a projection to begin with, and this is another projection. It might happen that the together, when you take the product, it might end up as a zero matrix in which no z will accomplish anything further. Okay, so it may happen that there is nothing left in that, okay, in the third term. If something is left, that is, if it is not the zero matrix, then you can still do something, okay. And if there is the third priority, then you can continue. If there is no third priority, that means after that the obvious priority of minimizing joint motion is there, then you put z equal to 0, that automatically minimizes delta theta, because you see this part, and this part are three orthogonal components, okay. And out of the three orthogonal components, perpendicular components, if you put one as one as 0 and other two unchanged, which you cannot change, then obviously you get the minimum size vector. So at the final stage, putting whatever z possibility is there, that as 0 will automatically minimize this. If there were a third priority, then we would try to satisfy that by this sequence of steps. Okay. So this is what you can do to do inverse kinematics on basis of priority of aspects of the task that you want to satisfy. Okay. Now, what about redundancy resolution in position domain? You may say that, man, we will go to the velocity domain later. Okay. We right now don't know the position itself. Okay. So you may try to solve inverse kinematics for a single position. You have to reach R and what theta would be correct. Now there are infinite thetas which can be correct. Now this is actually relatively a more difficult problem, because in the velocity domain you had linear equations. Here the equations are nonlinear. And nonlinear equations, you cannot use Newton-Raphson straight away because, or Newton's method straight away, because there are infinite solutions, out of which one has to be chosen. So there is a business for redundancy resolution. So you typically solve this problem by the formulation of an optimization type, in which you say minimize the joint motion from the present configuration to some configuration where it will reach R. So you minimize this subject to the inverse kinematics requirement being met and no collisions. This is one way. The other possibility is that rather than minimizing this, you can maximize the manipulability measure. And that's a good idea. Rather than minimizing the joint motion required, you can maximize the quality of the configuration with which you reach here. That's a good idea. So you can do that. That is, since there are infinite ways of reaching this position, we would love to reach by that configuration, reach at that configuration at which the manipulability is best. That is, we can best manipulate the algorithm, manipulate the manipulator, okay, manipulate the object. So this is when you have the task of inverse kinematics for a single position. Okay. Now it may be the requirement that you want to compute, you need to compute theta t for a complete path, r of t, not for a single position, for t running from initial time to final time. Okay. Now it may happen that RT, that is the full path in the Cartesian space at least, has been completely described. Okay. So that would mean that at each time step where the end effector is, that has been specified completely. Okay. In that case, this basically breaks down to a large number of problems of this kind, right? Because if R is completely prescribed, as in the trajectory of the end effector path has been completely given to you, then you discretize RT over time steps, and for every time step, you formulate a problem of this kind. Okay. And in that case, you typically would do this, because for a particular path in successive time steps, you would not take the risk of going from one place to very different place. Okay. So in that case, for every step, you would typically use this minimized joint version. Okay. The other possibility is that RT is the path of the end effector, like a welding curve, the curve along which you have to do welding. It is just take this object and place it there. Okay. So only the initial point is known and final point is known, and perhaps a few via points. Okay. The way trajectory planning you do. So if RT is prescribed at finite number of points, say starting, ending, that is R at Ti, R at Tf, and in between some 2, 3 other values of T, that is via points. If it is prescribed like that, then you have an optimal path planning problem. Okay? That is, you need to prescribe theta of T without knowing R of T. Basically, in prescribing theta of T, you end up defining an R of T, which will do your task satisfactorily and perhaps optimizing something. Okay. So that is actually some sort of a research problem. I said some sort of because it has been worked upon by people over 20 years. In fact, we made a lot of contribution. Our group made a lot of contributions in this. We have quite a few publications out of this particular work in addressing different aspects of it. Okay. First the basic formulation and then going on adding some more aspects. Okay, so here you have given RTJ at some values of J. Okay, say K plus 1 total number of time points. Okay, and you want to find out some continuous theta T from Ti to Tf, which will minimize this. This is our formulation. Okay, that is, this part half theta dot transpose W theta dot resembles a kinetic energy kind of term. Okay, which by on its own, if there is nothing else to impede its, nothing else like this to impede its work, then this would try to give you a straight path in the theta dot space, which will basically minimize the joint motion. Okay. Actually, this K is not required because the K here is actually creating confusion, because this K here means actually a scale factor. Okay, but that is not necessary because the scale factor could be included in this function P theta itself, and it is actually creating a confusion with this K, which is a number of points, number of time instance where R is known. So just ignore this K here. Okay. So just, but what is P theta? Okay. So here, this W is a positive definite, symmetric positive definite weight matrix as standing in the place of proper inertia matrix in the kinetic energy term. Okay. And this P of theta is actually a penalty function, which is high if theta is a C obstacle point, that is, if the configuration theta puts the manipulator at a collision course with some obstacle, okay, then it is very high. Then penalty should be very high. On the other hand, if the configuration theta is totally free from all obstacles, I mean quite far away, then it should be 0. And in between, in close encounter, it should have intermediate values, 0 to higher as it comes close. Okay. So that is the specification of a penalty function. Basically, it is a potential function, okay, which you saw in the potential field method of motion planning. Okay. But here it is used in a variational sense, something that I alluded to in my lecture on motion planning. Okay. So this penalty function has been put for obstacle avoidance. And in this Lagrangian formulation, it is actually playing the role of the potential energy. Okay. So, and this difference of the kinetic energy kind of term and potential energy kind of term, which is actually penalty function, this difference is the Lagrangian kind of thing. Okay. So, and its integral is the action which you try to minimize, very much in line with the Hamilton's principle of least action, subject to the inverse kinematics requirements. Okay, that is, at these time instants, theta must be something which map to the required R values at those time instants. Okay. So now you make a full variational formulation. I mean, either by finding the Euler's equation of this thing and then solve them, or discretize the thing at this stage itself rather than going up to the boundary field problem. Discretize it and get it in the form of a minimization problem of a large number of variables. Those variables being thetas at time ti, thetas at time ti plus something, thetas at time ti plus something more, and so on. That is discretized values. Okay, so n plus n plus n plus n, as many time steps as you use. Okay, capital N say. So then the total number of variables of the problem, of the optimization problem, will be capital N into small n. Okay, and these are the constraints which you use, and you can minimize the objective function. Big problem, but you can. Okay. So what should be the penalty function? Okay. In the potential field method, you saw that inside the obstacle points, C obstacle points should have very high infinite kind of value of the potential function, and much away it should be almost zero. So to make it smooth, you can have this penalty function. This is the form of the function that we used. So if it is free, that is, if the closest distance is d is higher than epsilon, then we say keep it very low, but we keep it differentiable smooth. Okay, so c0 by c3 plus this whatever. Okay, so where a large value of c4 makes this whole thing very small. If it is negative, which means actually interpenetration, okay, then this should be very high. Okay, that is achieved by putting a low C2. Okay, C1 is anyway reasonable, C0 is high, so this becomes very high. So for genuinely negative value of D, you have this kind of high thing. For genuinely positive D, you have this low thing, and you need something which is differentiable. I mean, if you need, because you will need to maximize, minimize this thing if you use any derivative based method. And if you are going to make the first order necessary condition Euler's equation formulation to put it in the form of a system of differential equations, then anyway, you need to differentiate it. So you want this to be differentiable at least once. So this genuinely negative and genuinely positive parts we break at minus epsilon and plus epsilon. Okay, and they are widely different. So what we do is that wherever at minus epsilon, wherever this segment ends, and at plus epsilon, wherever this segment ends, these 2 points, these 2 values and their rates, we match by a cubic from minus epsilon to plus epsilon. Thereby, this entire function, whatever discontinuous it may look, is mathematically rendered first order differential loop. Okay, that is, its derivative, first derivative is continuous, second derivative will not be, okay, because it's only a cubic. So this was our formulation and it works. You can have several variations of it. Okay, so this is the optimal path planning problem which addresses redundancy resolution through optimization of the path in the position domain. Okay, so this is where we stop, and in the next lecture I will try to give you a snapshot of analysis of parallel manipulators. Thank you.